So guys, as you can imagine, this fragmentation pattern is going to be pretty important, right? If we're basing the identification of these compounds on what they're doing at this electron beam, and we're looking at fragmentation patterns, we want to make sure that this is actually being done the proper way. So one of the very first jobs that you have to do when you use a mass spectrometer is do something that we call tuning, or you need to tune it up, right? So before we inject any samples for analysis, we want to confirm that the machine is actually tuned up and giving us the fragmentation pattern that we really should be seeing in the instrument. So, tune, 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 tune. Typically, the tuning process is going to be done daily, or at least it should be done daily. And sometimes with a company, it might be done twice a day, once in the morning, once in the afternoon. And if the machine's been turned off for quite some time, of course you're going to have to tune it to make sure that it looks okay. It's like calibrating an instrument. That's really what it's all about. It's like the balance, tearing it out to be zero. It's like the AA instrument, putting a blank in it to make sure it reads zero. It's like the UV, putting a blank into it, making sure it reads zero. This is our way of just making sure that this instrument's performing the way that it's supposed to be. So, number one, how do we tune it? Well, we turn the instrument on, if it's not already on. The problem is that this typically will take 1 week in order to accomplish. It's not just a machine that you can just go flip a button like the UV Viz, wait for a few minutes for it to warm up, and then start running samples on. The reason is because of the vacuum, right? That doesn't even look like a word. So that's supposed to represent the word vacuum. It's the vacuum that requires the pump. The pumping down and the vacuum basically getting almost to complete vacuum. And that will typically take at least 3 to 4 days. And then as it's pumping down, there's probably going to be a little bit of water, and there could be some nitrogen that's hanging around in the detectors and in the instrument that just basically needs to be driven off. So those extra couple of days is for the machine to make sure that everything is flushed out of it, all of the trace components of any kind of water or nitrogen's gone, and that it is ready to take a sample. It's actually advised to leave the machine running at all times. Never turn it off. The problem with us, though, is that doesn't make sense because we really only use the GCMS a couple of months out of a year. So we don't really want to just leave the machine on and have it waste electricity and have it waste the temperature and have it waste the gases as it's feeding itself. It's just a waste of money for us. But run it at all times. You do have to shut it down, though. When you replace the parts, vacuum pumps can go bad. The gas supplies can go down and they have to be changed. The pump oil's got to be replaced. All of those components, you're going to have to shut down the machine. There's no way around it. But it is encouraged for you to run the machine at all times and keep it going. That way it's ready to get a sample when you're ready to insert a sample on it. So we're going to say typically a week. At least that's what we give it. A week time to churn down, to prime itself, and get it to going where it needs to go. Now, after I turn the machine on, the very next step will be to tune it. Or if I come in and the machine's already on, my first step should be to tune it after that point. Again, daily basis. Think of it as blanking out the machine. The tuning is going to require a standard. In order for you to know if it's fragmenting properly, you have to inject a standard, and we should know the fragmentation pattern of that standard. Our machine uses PFTBA as a standard. It knows how that should fragment. It knows the abundances of the fragmentation patterns. It knows the numbers that it should be seeing. And if it doesn't see those, it's going to finely tune or adjust itself in order to provide us those numbers. If it needs to crank out a little bit of extra voltage, it will do that. If it needs to maybe tell you that it needs to have clean plates, then it will do that. But PFTBA is used as a standard, and that is why it's used. What does PFTBA stand for? The P stands for per, the F stands for fluoro, the T stands for tri, the B stands for butyl, and the A stands for amine. Perfluorotributylamine. This standard is located in a very small vial on the front of our instrument. You'll see that when you go into the machine and use it for the first time. And inside of this vial, there is a liquid, and that has the PFTBA in it. But that liquid is kind of volatile. So there's going to be some headspace that's up here at the very top. And this headspace is what's going to be injected onto the machine. It doesn't need any volume of liquid. The headspace is concentrated enough for it to do its job. That tells you how small these concentrations can be. That headspace will go into the machine. That PFTBA will go into the electron beam. It will fragment up. The detector will see those fragments, and it will give us a mass spectra. It will compare that mass spectra to what it should be. It will adjust everything according to plan, and then the machine has now been tuned. It basically gives us maximum detector response. That is what we're after in the tuning method. It ensures that the instrument will correctly identify the compounds. If it doesn't see the fragments, if it's not finely tuned, it might miss some fragmentation pattern, and it's going to give you a false identification because of it. So these things have to be tuned as much as possible. Now, do you want to see the compound of PFTBA? Of course you do, right? What does this compound look like? There you go. PFTBA right there on your screen. Notice that every single hydrogen is replaced with a fluorine. So typically, this would have been a carbon, and off of that carbon would have been a CH3 molecule. So that would have been a CH3 right there. But instead, it's a CF3, and that's a carbon. But instead of two hydrogens hanging off, it's two fluorines, and that's a carbon that has two fluorines hanging off. And here's a carbon. It's got two fluorines hanging off, and then we go to our nitrogen. And then off of this nitrogen, we basically see the same kind of repeat. So there's kind of the third unit, or the second unit, and this is the third unit. So there we go. So just imagine in a normal organic molecule, all of these Fs will be hydrogens all the way around, and nothing would be special. But this molecule has replaced every single hydrogen with a fluorine. So super, super large molecule here that we are using in the mass spectrometer system. Notice up here at the top, PTBFA. That is the most potent greenhouse gas ever discovered. Still is, I think, till today. 7,000 times greater than carbon dioxide. So in that small little vial, in the front of our mass spectrometer system, we have a liquid solution that is 7,000 times worse than carbon dioxide. And we are opening that vial up to allow this machine to take that compound and destroy it and break it apart into fragments. And that is what it uses to determine if it has a proper signal or not. And if it doesn't, it will adjust itself so that it does. Kind of scary. We're putting you in the hands of a greenhouse gas 7,000 times worse than carbon dioxide. Don't tell any of those green protesters about it. So after we run the tuning, this is typically the information that we would see from the instrument. It looks kind of scary, doesn't it? There's a lot of information on here, and there's a lot of information that we're going to have to suffer through. But this is the problem of the mass spectrometer system. There's so much data, there's so many things that I need to take away from it. It's really kind of hard to start sometimes on what is what. Down here at the bottom, this is what we would typically call a tick. So let me go back with that. And that's basically, we'll talk about it in a little bit later, but this is the total mass spectrometer data is what I would see down here at the very bottom. So notice here at the x-axis, we have numbers that range from basically 0 all the way up to 700. These are basically numbers that represent molecular weight or formula weight of a compound or a fragment. Notice that each line here, each one of these represents some type of fragment, and that fragment could also be contributed to isotopes as well. So the machine will look at these signals that it's getting, and it will look at the height of the signals. Notice over here to the top, think of it kind of like an abundance, even though it's not really, but think of it as kind of like an abundance or an absorbance. Just the signal layout, and everything is compared to the tallest. Here's the tallest. So that's why that one is at 100, and then everything else is compared to that one. These small little tick marks down here at the bottom, we now know why those are present. Those are all present due to isotopes that might be found in the compound itself. So that's why those are going to be there. Notice there's 3 that it will look at mainly. There's this 69 fragment, and then a 219 fragment, and then a 502 fragment. So the 69 fragment is going to be this big one right here. The 219 is going to be this big one right there, which is the tallest. And then this 502 is going to be this one down here at the very end. So those are the 3 that it looks for. Notice it says the abundance right here to the side. The relative abundance, after it does the signal, it kind of looks at that and it says, well, hey, this is kind of the tallest one, and everything else is going to be compared to it. And then it gives us some other information, too, that we don't really have to worry about. Up here at the top, it's the same kind of story, but this is not the total. Down here at the bottom is the total chromatogram, or the spectrum that we would see. Up here at the top, they're just focused on those 3 areas. So that's why you're seeing a 69 and a 218 or 219, and then a 501.9 or really a 502. So these are just kind of snapshots of the 3 major ones that you're looking for, and you're seeing those enlarged on the screen up here at the very top. So this peak is this one. It looks like a line right here, right? But what they've done is that they've taken this and they've enlarged it and zoomed in. So they're kind of telling you it's not really just a line. I mean, this is actually a peak that comes up and comes right back down. The same thing happens here at 219. Like, this is the zoomed in version of that line that's on the spectrum. And then this one, of course, is the same way. This is 502. And that is representation of that line that looks just like a straight line up and down. That's all there is. But when you zoom in, it's actually looking like a peak that we would see from some of our chromatography systems. Over to the right-hand side, you'll often see this type of data. It says mass gain, mass off, emission, filaments, repellers, ion focus, PFTBAs, open, sample sizes, MS source, MS quad. All of these are numbers that relate to a certain piece or part in the machine and how it works. What you need to stay focused on, though, is lens number 1. Lens number 1 is going to provide you with how dirty your mass spectrometer is. And it should be close to 0. If it's close to 0, then it's pretty clean, and I can feel good about using this machine after my tuning file happens. If it's not close to 0, then this probably means that you need to clean the instrument. Maybe you don't need to clean it that day. Maybe it will still work, everything will be fine. But you will eventually need to clean that lens off because there's going to be some buildup that can happen over a course of time. And you do not want that to happen. You want these things to stay as clean as possible. No contamination. So lens 1 on our Shimatsu instrument will basically be looking at the cleanliness of the instrument. So keep that in mind. And when we do our first tuning file together, I'll show you where to find that information. So here's more about the tuning file. The tune will look for 3 peaks. We've already talked about what those 3 peaks are, 69, 219, and 502. And what it does is that it takes these 3 peaks and it will calibrate itself. It adjusts the resolution of the instrument. So can it determine the difference between C12 and C13, yes or no? And it will adjust the peak height for quantitative work. So basically it shoots that compound in, it looks how high those fragments become, and if it's not happy with the height of that signal, then it will increase what it needs to increase in order to get the signal height at the proper dimension. How does it do that? How does it adjust itself? Well, it varies the voltages. Within the detector, it varies the voltage until it finds kind of this proper Goldilocks area for it to use. There's a couple of lenses that we want to talk about and repeller plates that we'll talk about in the machine eventually, but not yet. But there's 4 of them. An entrance lens, an exit lens, a repeller, and an ion focus. So the entrance lens places a positive in the middle of the stream. The exit is a positive in the middle of the stream. Repeller pushes the positive through the machine, and the ion focus places the positive in the middle of the stream. So basically what we're talking about is that when this compound comes in to the electron beam and it gets slammed with that energy, and it creates this fragment that is now positive, we want this positive piece to go straight through the middle. We do not want the positive piece to kind of deviate either up or down on us, because the detector is never going to see it. And the reason is because on the other end of this tunnel, there's going to be an exit door. And that's kind of where the exit lens is going to be. The repeller pushes all of these positives down the tunnel. So that's where the repeller's coming into place. And this ion focus just kind of helps it stay in the middle as it goes down this tunnel and out the other end. Now, tunes will also provide an idea of any leaks. So if I go back to this tuning file, so notice on this spectrum down here at the very bottom, there's a couple of peaks that I would see there. Again, the 69, the 219, the 502 is really what we're focused on the most. But if there is contamination, such as the presence of O2, CO2, or N2, all of these are components of air. The atmosphere that we breathe, the air that we breathe in the room, is composed of nitrogen, carbon dioxide, and oxygen gas. If I see those present in the actual tuning file, that's a very good sign that I have a leak. Air is inside of the machine, air is escaping on the inside of the machine, and I need to make sure that I can find that hole and plug it, because I'm not going to get very good data if I do. Now, it could be just air trapped into the machine that needs to eventually be pushed out because you've had it off for so long. And if so, that just means keep the machine on and let it get warm and toasty for a little bit. That's all that means. But I can also see water as well. Again, water can also come from the air. It's just moisture. I can't really have that moisture present in my mass spectrums. It starts to do funny things with the fragmentation pattern, or spectra. There's no such word as spectrums. It's spectra. And it does funny things with the mass spectra data. So I want to make sure that all of the water is gone as well. So that's going to be a problem, but that's also one of the reasons that we tune. If I see very large signals that happen at these areas, then that means I have a leak. Where is that leak coming from? Typically the vacuum door that I can open to do some maintenance on it, or column fittings that go into the machine. Those can spring leaks, and over a course of time, those rubber O-rings and those fittings can wear out, and I'm going to have to replace them. So I want to make sure that none of that is going to be present. Now, if I take a look at these formula weights, water, of course, is going to be around 18. And what you'll find out in mass spec is that we typically report formula weights in terms of whole numbers. Okay, the nitrogen gas is 14 and 14, which is 28. The CO2, well, that's going to be 16 and 16, which is 32, right? And then another carbon, which is another 12. So this is actually going to end up being a 44. And then the oxygen is going to be 16 and 16, which is 32. So these numbers are very important on a mass spectra system. So for example, if I have water in my system, what I would see is a taller peak that would happen at 18. And if I see that, then that means there's some water still left in my system that needs to be pumped out of there. If it's been turned off, I'm going to expect it to be there. If it's been running for a course of time, though, and it's always been running, and now magically I see that this is showing up, then I have sprained a leak in the system. The same thing happens with all of these others as well. My 28, my 44, and my 32. All of them are going to kind of cluster down here to the bottom left. So that's kind of an idea of the tuning file. Once the instrument's tuned, it applies the proper voltage to the instrument. And again, that proper voltage is making sure that it is equivalent to about a 70 electron volt. And that is very important. This is how we compare our fragmentation patterns to the database. And if we're not running at 70 electron volts, then it's doing us no good. We're not going to be able to identify anything because our settings are not proper. Okay? So that's the story with tuning file. Again, we should be doing it all the time. The tuning file should have its own logbook. We do actually have one, believe it or not. And this helps you keep a record of the tuning files and when they were done and who did them and the data that's coming from it. And the funny thing is that we had Shimatsu to come out one time, who is our maker of our GCMS system, and they were really concerned with dirtiness. It was our vacuum pump, right? Our vacuum pump went out, and they were like, oh, are you really tuning it? When's your last tuning file? You know, they thought they got us. Well, little did they know that we had this logbook, and we pulled out the logbook of all of our tuning files that basically had daily tuning files that we were doing at a regular basis. And we were able to track the date that that lens became dirty all the way up to where we began to get a problem. And then after they came and maintained it and cleaned it and left, then we did another tuning file, and that lens number 1 plummeted down to close to 0. So that proved that they actually did their job. But it also gave us about 5 years worth of tuning file data that we could go back and show them this is where we started having a problem. Okay, so it's pretty nice to have things like that, especially in a company, especially if you're regulated. These types of things you should know, and these types of things you need to keep your eye on. So that's very important, and that's the purpose of tuning, getting the machine ready, and this is your first introduction to mass spectra. So again, I hope you got your belt buckles on. We're going to be along for a bumpy ride.